We've all gone through periods of high stress, but next on How It's Made are machines specifically designed to ramp up the pressure. They are force testers, machines designed to pull and compress products to breaking point, used to test the integrity of products and verify they have what it takes to laugh in the face of pressure. Force testers are built to pull and compress things. Here, the tester arm bears down on a pencil. It determines how much force can be applied before the pencil bends or breaks, and it displays the measurements on a screen. In the 1930s, basic force gauges were attached to cranes to measure a product's strength. But today's force testers are very high-tech and feature digital displays and computerized controls. Production starts with the steel base. A technician screws brackets for the main computer board to it. He then installs the computer board using nuts called standoffs that raise it above the steel plate. This creates an airspace between the two, preventing electrical shorting. Throughout the assembly, the technician wears an electrostatic discharge band on his wrist. This arrests static electricity to prevent damage to the parts. The motor drive board is screwed to the force tester base before the next parts are added. They include the power supply board, a mechanism to turn the unit on, and an emergency stop assembly. The technician routes the wires for the power switches and installs the push buttons. A ribbon cable is connected to the main circuit board. Then the other end of the cable is connected to the motor drive board. This allows them to communicate. And finally, the power supply connections are completed. Another member of the team now assembles a vertical support rail to an aluminium base. This rail is essentially the backbone of the tester. It will support the force arm and the track it moves on. The track is screwed to the support rail. Using an alignment tool, the shuttle is slid into the grooves of the track and checked to see that it moves freely up and down. The force arm is now ready to be mounted on the shuttle. The technician inserts a long threaded rod known as a lead screw into the force arm and fastens it to it. The lead screw will rotate to move the force arm up and down. He lowers an aluminium cover over the force arm assembly and secures it to the base. One side of the casing is open. An accordion-style rubber curtain will be installed to this part later. Next, a rubber belt is threaded around a pulley attached to the end of the lead screw. The motor is then installed and the other end of the rubber belt is wrapped around the motor pulley. This motor drive assembly is what will turn the lead screw to move the force arm. The technician now mounts the base with the electronics to the force tester frame. He connects the switches for limiting the force arm's range of movement. And he installs an encoder on the motor to provide feedback on speed and power. The electronics are covered with a tough plastic casing. Then a slotted table is placed on the unit. A computer tablet is attached to the tester. An adjustable bracket is included for changing the screen's position while it's being used. A force tester doesn't just bear down on things, it also pulls things apart. A technician conducts a pull test on a piece of nylon cord. He activates the force arm. The force arm pulls the cord as it's gripped at the base. The tester measures the peak force required to pull the cord apart. And the results are displayed instantly on the control screen. There are different force testers for different applications, but the purpose is always the same: to pull and compress objects in order to test their limits. So, the next time you sit down and break your plastic chair or your shoelace snaps, you'll know that they've never met the force tester. One of the many ways manufacturers can package a product is in a composite can, a cylindrical container made of cardboard with a moisture barrier lining. Composite cans are less expensive to produce than glass or metal containers, and of course, they're just as recyclable. Everything from axle grease to Parmesan cheese has been packed into composite cans. The cans are cardboard, with an interior lining that prevents it from absorbing moisture. The top can be a sifter, a pull-tab cap, a ring and plug, or a peel-off foil. The process starts with a thin strip of paper coated with either foil, plastic or wax, which is wound over a long steel rod called a mandrel. The machine applies glue to the top of the strip. Simultaneously, 2 strips of cardboard wind off rolls and pass over a glue applicator, which coats the underside with adhesive. Then, these twin overlapping strips wind around the coated paper wrap mandrel. The glue bonds the layers, producing a 2-ply cardboard tube with an interior moisture-proof lining. The machine pushes the tube off the mandrel to an automated circular saw, which cuts the tube into shorter pieces. They fall into a bin, which feeds the labelling machine. Suction cups pick up the sheet of labels and run it over a glue roller, which applies adhesive to the backside. Then, a vacuum carpet carries the labels onto another set of mandrels. The machine slips the tube onto it and then wraps the labels around the tube. Next, knives cut the spinning tube into cans. A pusher moves the cans off the mandrel onto a conveyor towards a device called an upender that stands each can upright. The cans then spin through a gluer which applies a bead of adhesive along the top rim. Meanwhile, another station lines up the lids in single file. These cans are for Parmesan cheese, so the tops are plastic sifters. They're placed one by one on a carousel. The timing is choreographed so that the tops align with the cans fed to another carousel. A plunger pushes the top about a centimetre down into the glued rim of the can. As the cans exit the machine, a conveyor turns them upside down. The cans reach the end of the line, where they're stacked on shipping pallets. The Parmesan cheese producer will receive them like this, open end up, ready for filling. To make the metal base for the can, a punch press stamps circles out of a strip of tin that's been coated with a food-safe lacquer. This gold-coloured coating prevents the tin from rusting when it comes into contact with the moisture in the cheese. The next machine curls the edge of each tin circle with forming rollers to shape a rim that will grip the can. This production line is making composite cans for grease cartridges, which mechanics use in a device similar to a corking gun. For this product, the cardboard tube has a plastic-coated rather than foil-coated liner. The liner is heat-sealed rather than glued to the cardboard to prevent the grease from leaking out. The lid is a rigid aluminium top that you remove with a pull tab. This machine, called a seamer, crimps the metal edge tightly around the can's rim. As the cans exit the machine, a computer takes measurements of each top. If it doesn't meet specifications, the machine automatically ejects the can from the line. The cans that pass inspection continue onto the packaging area, where they're picked up through the open end with a multi-pronged fork and inspected one last time prior to shipping to the grease manufacturer. For us at home, once a composite can is empty, we can separate the cardboard from the metal, rinse it off, and throw them into our recycling bins. And now you could say this item is in the can.